ISRO's solar mission, Aditya L1, is an ambitious project with very specific objectives in mind. Let us look into it to understand the mission better. The major science objectives of this mission are: first, to study solar upper atmospheric dynamics. The chromosphere and corona are two distinct layers of the Sun's atmosphere. The chromosphere lies just above the photosphere, emitting a reddish glow during solar eclipses due to the presence of hydrogen and other elements. Beyond the chromosphere lies the corona, a region of extremely high temperature and low density, visible only during total solar eclipses or with specialized instruments. These layers play crucial roles in the Sun's energy emissions and are subjects of intense scientific study. Second, to study chromospheric and coronal heating, physics of the partially ionized plasma, initiation of the coronal mass ejections, and flares. Partially ionized plasma, a complex state of matter, results from the interaction of high-energy particles with gases, causing some atoms to lose electrons. This process leaves a mix of charged ions and free electrons within the gas, enabling it to conduct electricity. This phenomenon is essential in various astrophysical and laboratory contexts, contributing to our understanding of celestial bodies' behavior and aiding in the development of advanced technologies such as plasma-based energy sources and propulsion systems. Third, to observe the in situ particle and plasma environment, providing data for the study of particle dynamics from the Sun. Particle dynamics from the Sun encompass the intricate interplay of charged particles, predominantly electrons and protons, emitted during solar processes like flares and coronal mass ejections. These high-energy particles traverse the vacuum of space, are influenced by magnetic fields, and interact with the Earth's magnetosphere, potentially affecting technological systems and posing hazards to astronauts. Studying these dynamics yields insights into space weather phenomena and enhances our ability to predict and mitigate their impacts on Earth and space-based assets. Fourth, to understand the physics of solar corona and its heating mechanism. The solar corona, a luminous outer layer of the Sun's atmosphere, presents an intriguing puzzle in astrophysics. Despite the cooler photosphere below, the corona exhibits temperatures exceeding 1,000,000 degrees Celsius. This stark contrast between the Sun's surface and its corona, known as the coronal heating problem, remains enigmatic. Proposed mechanisms, such as magnetic reconnection and wave heating, suggest that the Sun's magnetic activity and intricate plasma interactions play pivotal roles in energizing the corona and driving its exceptional heat. Fifth, to run diagnostics of the coronal and coronal loops plasma, temperature, velocity, and density. These loops, prominent features of the Sun's corona, consist of magnetically confined plasma. Its temperature within these structures can soar to millions of degrees Celsius, indicating extreme heat compared to the solar surface. This superheated plasma's intricate motions, governed by magnetic forces, manifest as high-velocity flows. Additionally, the loops exhibit varying densities, showcasing regions of concentrated and rarefied plasma. Sixth, to understand the development, dynamics, and origin of coronal mass ejections. CMEs are potentially disruptive solar events. These intense bursts of solar wind and magnetic fields are ejected from the Sun's corona, propagating into space at high velocities. They possess the power to impact Earth's magnetosphere, leading to geomagnetic storms that can disrupt communication systems, power grids, and satellite operations. Understanding these is vital for space weather forecasting, ensuring preparedness for their potential technological and societal impacts. Seventh, to identify the sequence of processes that occur at multiple layers which eventually leads to solar eruptive events. These eruptive events, also known as solar flares and coronal mass ejections or CMEs in short, are fascinating phenomena originating from the Sun's dynamic magnetic field interactions. During a flare, the Sun emits intense bursts of energy across the electromagnetic spectrum, including X-rays and radio waves. Moreover, CMEs can impact Earth's magnetosphere, potentially causing geomagnetic storms. 8th. To study magnetic field topology and magnetic field measurements in the solar corona. The solar corona constitute critical components in our understanding of solar activity. The complex interplay of magnetic fields influences phenomena like solar flares and coronal mass ejections, impacting space weather. Utilizing advanced instruments and techniques, scientists will analyze the corona's magnetic field structure, shedding light on its intricate behavior. These insights enhance our ability to predict and mitigate potential disruptions caused by solar events. 9th. To understand the drivers for space weather, origin, composition, and dynamics of solar wind. This wind, an integral component of our Sun's extended atmosphere, originates from the corona, the outermost layer. Comprising charged particles, mainly electrons and protons, it emerges due to the Sun's high temperature and intense magnetic activity. These particles are emitted into space at incredibly high speeds, forming a continuous flow that permeates the solar system. This dynamic stream influences interplanetary space, sculpting planetary magnetospheres and contributing to the phenomena observed in the broader cosmic environment. We hope ISRO finds success in the mission. Click here to watch the highlights of ISRO's lunar landing. Or you can click here to learn more about the Aditya L1 mission.